Hey, QED coders, this is Michael. I, uh, I don't think that Jan is going to be able to join us today, but got something interesting that I want to share anyway. Um, so we just had our daylight saving time change here in the United States, and that got me thinking about time and about synchronizing clocks and about this cat that's probably going to jump up on my shoulder. Just give me a little bit of warning before you do, please. And that put me in mind of my, I would say now second favorite, well, no, let's not choose favorites, math paper. This one by Leslie Lamport, Time, Clocks, and the Ordering of Events in Distributed Systems. Um, I used to run the Dallas chapter of an organization called Papers We Love, and that was a group that would meet once a month and present on different math papers or research papers or just um, any form of research that they really got a lot of value out of and wanted to share with other people. And so, of course, anytime that I got in front of folks, I was talking about the mathematics of software. So I was talking about Leslie Lamport. I was talking about um, uh, uh, Mark Shapiro. I was uh, I was talking about the cap theorem. I was just Paxos, everything, and and so this was one of the papers that I presented. So, if you will indulge me, I pulled up the presentation that I made for that paper, and went back through the paper to refresh my memory. It's one of those papers that I return to and I read every so often. So I would like to share that with you, if you don't mind. So let's get the screen share going, just in case we have anybody joining the stream a little bit late. And then we can talk about time, clocks, and the ordering of events in a distributed system. So this is probably the most famous of Lamport's papers. It was an early one, and I've heard interviews with him where he said that what people get out of it surprised him. That he was writing about state machines, and people are talking about getting the ideas of vector clocks and causality and those sorts of things out of it. And it's like, no, I'm talking about state machines in here. Um, and I'm guilty of that too. What I get out of this is primarily the idea of causality, a specific definition that I find extremely useful. And so that is the spirit with which I've gone on and taken these ideas. But let's go through the paper as it is presented. So this is a very short paper, actually. You can find PDFs online. It's 7-9 pages. It's really short, but really dense. There's a lot going on in there. So let's start by talking about distributed systems. So Lamport defines a distributed system as a collection of distinct processes. So this was actually before the collaborating. What was the idea of collaborating processes is, and then putting the model together about how they collaborate, the Tony Hoare work. But this is the definition that he starts with. It's a collection of distinct processes spatially separated. That was actually quite significant to him as I listened to one of his interviews. Which communicate with one another by exchanging messages, and that's a distributed system. So processes on the same machine are not part of a distributed system because they are not spatially separated. And the reason that spatial separation makes a big difference is actually related to relativity. I got this feeling of special relativity while reading the paper, but when I watched an interview with Leslie Lamport, he mentioned that he um, he found an error in a previous paper and corrected that error in this paper, and that error became obvious to him because he was thinking in terms of special relativity. So the idea in special relativity has to do with the fact that all motion is relative and the speed of light is constant in any reference frame. So what's special about special relativity is that those reference frames are not accelerating. So you've got an observer who thinks that he's just standing on the ground, and you've got he's seeing a train speed past. The people on the train think that they are sitting still, and they see this person outside their window speeding past in the opposite direction. Now, two events happen: one before in front of the train, one behind the train, A and B. And the observer on the ground sees them happen at the same time. So those two flashes of lightning, A and B, are exactly the same distance away from them, and light propagates from those at the same rate, and so therefore they see those flashes of lightning at the same time. Now, the person on the train is observing those same two flashes of light, and even when they are right there in the middle, right between the two, they see something different than the person on the ground. So why is that? Well, if this person is moving at 3/5 the speed of light toward A, how fast does the light from A propagate to them? Did you say 1 plus 3/5? Nope, it propagates at the speed of light. The speed of light is constant. So, so the middle of the shock wave, if you might say, of A, the middle of that light cone expands out from that point A relative to the person on the train, and then it's not that the light adds to their motion, it just propagates toward them at the speed of light. Meanwhile, the light from the flash behind them propagates to them at a different speed, or at the speed of light as well. So not 2/5 the speed of light, as you might imagine. So how much time does it take to get to them? So that depends upon their speed. It doesn't. The distance actually has to change in order to make distance over time work. But yeah, you can see that that they would perceive the light from A as reaching them before the light from B. And so they would see those two events as happening at different times. So I'm not doing a fantastic job of describing this. There's a YouTube channel called Floathead Physics that I recently discovered, and Mahesh does an excellent job of describing this. So please check out Floathead Physics. The point is that we think about A and B as happening simultaneously, but from the point of view of the observer Y, they do. From the point of view of the observer X on the train, they don't. A happens before B to the observer on the train. And so, why, we can't talk about the time at a place if that place is distant. So go back to distinct processes spatially separated. We can't talk about the time at that process if that process is spatially separated from this one. So this would tell us that maybe this whole idea of measuring time in a distributed system is flawed. Maybe there's no way to accomplish it. Well, let's hold on to that thought, because I think Lamport has something interesting to say about that. Before we get there, Lamport goes through this idea of total ordering versus partial ordering. So I've talked about this on my channel before. That was a video long in the past, so let me do another coverage of that, specifically using the language that's in Lamport's paper. So for total ordering, you've got a pair of events, A and B, like these events here. And you might be able to say that A happened before B, or you might be able to say that B happened before A. So if these events are totally ordered, one of those two things is true. A before B or B before A. We'll ignore the fact that A and B could be simultaneous. We'll say that these are distinct events. Now, the transitive property holds that if A happened before B and B happened before C, then A happened before C. So this happened before relation is transitive. So let's talk about some sets that are totally ordered. You might think about the counting numbers. That seems like a totally ordered set, and in fact, it is. So as you count, you go to the next number in the sequence, you pick any two numbers, and you can say 3 and 5. 3 came before 5, and that is absolutely true. The transitive property holds. If 2 came before 3 and 3 before 5, then 2 came before 5. Perfect. There are no two numbers that you could pick that you can't say which one came before the other. These are distinct events. So you're not measuring 3 against itself. You're talking about distinct events. And so this is a totally ordered sequence. Now compare that with partial ordering. So in partial ordering, for some pairs of distinct events, A happened before B or B happened before A, what about the others? There are some others for which you can't say either of those two things. You can't put them in order. How about the transitive property? Yes, the transitive property still holds in partial ordering. If A happened before B and B before C, then A happened before C. But if you can't say whether A happened before B, then you learn nothing new by knowing that B happened before C. The transitive property doesn't tell you anything new about something that you didn't already know if you didn't know the ordering. But if you do know the ordering, transitive property holds. So, what kind of sets are partially ordered? You might think about build dependencies in a build system. So maybe you've got a Visual Studio solution and it contains several different projects. So you've got your application solution or your application project that depends upon library A and library B. And then both library A and library B depend upon a common library. And so the build order that you choose has to be common first. And then you can choose library A or library B once common is built, but you have to build them both before you can build the application. So this is a partial order among the projects. Since application depends upon library A, then we know that library A comes before the application. Neither library A nor library B depend upon each other, so therefore neither one comes before the other. So we could choose to build them in either order, and everything's fine. Transitive property holds. Common has to be built before application because libraries A and B both depend upon it. And so now you can choose a total order that satisfies the partial order. So assuming that your machine can only build one process or one project at a time, we'll get to processes later. Assuming that it can only build one project at a time, it has to choose library A or library B first. There are two valid choices. There are two valid total orderings of this build process, both of which satisfy this partial ordering. By the way, this isn't a word that Lamport goes into in the paper, but that is called a topological order. So whenever you find a total order that satisfies a partial order, that's topological ordering or topological sorting. I would say that about 5 of my biggest projects have really just been topological sorting in different forms. Go back to Assistikit. That's all it does, topological sorting. All right, so that is an example of partial order. Now, whether you define a total order or a partial order, you can use that to define this idea of happened before. So, suppose you have a set of processes, some fixed number of processes. He stays with this fixed number idea for the duration of this paper. If we want to vary the number of processes, have processes come and go, that work comes later, but this is setting the groundwork. So you've got a fixed number of processes. We'll label them P0 all the way up through Pn. And now A and B are 2 steps within those processes. So you can think of a process as the execution of some code. And so it's going to take some steps in order to perform those executions. And processes are sequential, so those steps are totally ordered. So you would say that A and B, if they are 2 steps within the same process, then you could tell that A came before B because of that sequential ordering. So if that process is PI, that first bullet point tells us that if PI, that process executed A before PI, that same process executed B, then A came before B. That's the easy part. Now let's talk about the more interesting part of this. So A is the step that process I is sending a message, and B is the step that process J is receiving it. So if PI sends a message and PJ receives it, then the sending of the message happened before the receiving. A happened before B. That's the second bullet point. And then the third bullet point, you might recognize that one. That's the transitive property. So happened before is transitive. So this is how Lamport defines the happened before relation. And it seems like a pretty solid relation. Don't see anything wrong with this definition. But as it turns out, this definition is really all you need in order to come up with some really interesting things. So, for example, let's talk about causality. Causality is a stronger concept that that something wouldn't have happened otherwise. So if A caused B, then you might assume that if A hadn't happened, B wouldn't have happened. Now, it's really hard to prove that, and so we don't work at that specific level, although we may take on some of that nomenclature. But what we can be certain of is that A cannot cause B unless A happened before B. And so this was one of the errors that Lamport spotted in that prior paper, is that it violated causality, that it was possible within this algorithm for something to cause something else without being able to prove that it happened before something else. And so that would seem like you're going back in time, or that would seem that that spatial or that special relativity is not holding up for you. So we can't violate causality even as we order our events in a process, or steps. So a process is a totally ordered sequence of events, as we said. And so you could say that within a process, it has the potential of each step causing the next step. And a lot of times that's true. So I assign a value to a variable, and then I use that variable. So the effect of that usage of the variable wouldn't have been the same had I not assigned that value. So you've got that causality. But what we are really concerned with and what we're going to be proving things about is just the ordering. So in order to be able to prove things just based on ordering, we're going to define the term concurrency in a very distinct, unique way. Concurrent events are events that have no ordering between them. Now, you might think about concurrent events as events that happen at the same time. You might think that you have to be able to prove that these two flashes of lightning happened simultaneously in order to call them concurrent. But special relativity tells us there is no simultaneity at a distance. That's the relativity of simultaneity. And so you cannot call two events concurrent based on the fact that they happened at the same time, because at the same time has no meaning in a distributed system when you have processes at a distance. And so you might think that, okay, so that top one is one process, that bottom one is another process. That part is clear, because if they were the same process, there would be an ordering between them. Processes are sequential, they're totally ordered. So these must be different processes. Great. And so you might think that if the process A, you number the processes, if process 0, if that event happened at the same time as process 1, the event on the bottom, then once the clock ticked forward for process 0 and we executed the next step, that one would no longer be concurrent. It can't be at the same time. But that's not how this definition works. This definition just says that the events have no ordering between them. And so if that next step in process 0 also has no ordering with this step in process 1, then it is also concurrent. So two steps can be concurrent with a third, even if they're not concurrent with one another. So that's a different way of thinking about the word concurrent than we usually do, but this is the mathematical precise definition that Lamport writes down and uses. And he doesn't deviate from this. So that's the one that we're going to use. So that's how we think about concurrency in these systems. So now let's return our attention to a distributed system that's a set of distinct processes that are spatially separated that communicate by exchanging messages. So we've got a sequence of messages in process 0, a sequence of messages in process 1. We can tell which ones came before the other because of those arrows. Now we've got one of those steps in process 1 is sending a message, and then there's another step in process 0 that's receiving it. And then the opposite happens. Process 0 sends a message and process 1 receives it. So this is a valid partial ordering of the events in a distributed system. And it's defined by this happened before relation. So now, now that he's laid this groundwork, he wants to define a useful tool that he calls a logical clock. So what we're going to do is, remember, we have a fixed set of processes. That's important for this definition to work. We have a fixed set of processes, and we are going to define a clock per process. So process I gets the clock Ci. And Ci of A is the value of that clock at event A. Event A being a step in process I. So the clock conditions. Well, we're still part of the clock definition here. So that Ci of A increases for each event. So that Ci of A is greater than Ci of B if A happened, or if B happened before A. So so the value of the clock increases. So you might think about it as a sequential timer, just an incrementing number. That's a good start, but that's not what this demands. It just demands that it's increasing. Now we can combine two clocks. We can combine n clocks by taking C0 through Cn, each one of those Ci's, and we can combine them into this one distributed system clock, this one overall clock Ca, where A is any event that happened in any of those processes. So, so if this event happened on process I, we can say what is the value of this clock at that event. So notice the locality of that definition. The event happened at a process, so we can tell what the value of the global clock is at that event, at that process. We don't need to talk to the other processes in order to learn the value of the clock. That's an important thing. Now, let's talk about the clock conditions. So for any pair of discrete events, A and B, if A happened before B, you know, I think I got that greater than backwards in that first one. Yeah, because the arrow means A happened before B. All right, so yeah, now I've got the relation correct here. If A happened before B, then CA is less than CB. Now, this isn't CIA and CIB. We are talking about discrete events now that could be in any process, even in different processes. So, for this clock to be correct, we have to be able to evaluate the clock at that event on this process, evaluate the clock at a different event on a different process, and know if one of the events happened before the other, that the clock is less than the other. So less than maps to happen before, and it tells us that that's true. That is asking a lot of this logical clock. You have to be able to evaluate it locally. It has to represent happened before, yeah, that's and it has to be constantly increasing. So this is a useful tool that he came up with to then prove some interesting things. So let's talk about how he makes this clock increase. So I think I heard something. Let's just make sure that, yeah, it must be something else, not somebody trying to get in touch with me on the stream. Okay, let's talk about how these clocks increase. So each process increments Ci between each event. And now since Ci is part of C, that means that it's incrementing that part of C with each event. But we didn't say anything about the other parts of C, so let's talk about those. So when PI sends a message, it includes the timestamp. That timestamp is the CI component of its knowledge of the clock. And it says that is TM, that's the timestamp of that particular message. And then when PJ receives M, then it updates its own clock, CJ. So, so CJ is the maximum of either the timestamp that that it received in the message, plus a small delta, so that it's greater than that message, or the clock CJ itself. So the clock will jump forward if the timestamp is greater than its own clock. And so that is going to continue to push the clocks forward. Let's see how that plays out. So let's suppose that we were to represent CI as these numbers, and so we can see that P0, it's just doing 2, 3, 4, 5, 6, 7, 8, 9. It's just a sequential list of numbers. So each of the events in P0, we can tell which one happened before the other. In P1, we happen to have the clock CI starting at 4, and then 5, and then 6, and then step 7, where the clock would typically be 7, it's receiving a message. So now it checks the timestamp of the message, which was 4, and then it takes the max of 4 plus delta, we'll call the delta 1 in this case, and its current clock. And it says, well, 7 is still the max, so I stick with 7. And then it continues on, 8, 9, 10, 11. Now process 2, it's ticking along until finally at after step 6, at what would be step 7, it now receives a message with the timestamp 8. So 8 plus the delta is 9. 9 is greater than 7. 9 becomes C of 2. And we keep on going. So we have this idea of an incrementing clock. And this incrementing clock is satisfying the happened before relation that was defined at the beginning. And we did this all with just numbers. This is pretty cool. So it satisfies the condition, because if A and B are in the same process, then CI of A is less than CI of B. That's simple. If A is sending a message and B is the receipt of the message, then because we're using the max operation, CI of A is going to be less than Cj of B, because we're adding a delta. So either way, we satisfy the clock condition. No matter where you are, the clock at A is less than the clock at B. Now what's really cool is that we didn't invoke vectors. We didn't keep track of all the other events, all the other processes within the system. What's interesting, and in fact I found myself just now making that same mistake, is that people will read this and they will think, oh, this is about vector clocks. Vector clocks came later. In one of the interviews with Lamport, he was saying that people come up to me and say, yeah, like that paper, when you introduced vector clocks, I didn't talk about vector clocks, I talked about state machines. Vector clocks aren't even in there. But this is where it kind of looks like vector clocks. So let's see if we can apply this logical clock to the mutual exclusion problem. So we've got a distributed system, and we have a single shared resource. How do we know that we can satisfy mutual exclusion? We need an algorithm that satisfies 3 requirements. So we need to know that the resource that has, or has the resource, or the process that has the resource must eventually release it. The requests to grant the resource are the resource is granted in the order that the requests are made. That's a sticky one. And then, if every process which is granted the resource eventually releases it, then every request is eventually granted. So you can kind of think about this as, let's suppose you go into a bakery. Actually, Lamport uses the phrase bakery algorithm to describe this idea of mutual exclusion. So you request a resource, so you take a number, and the requests are granted in the order in which they are made. So the person that took the number 2 is going to be served before the person who took the number 5, assuming that the ticket machine spits out those numbers in increasing order. So let's use the logical clock as the stand-in for the ticket machine, and then we can solve this problem. It's pretty cool. All right, so let's do that. We've got our logical clock, And we can see that we've got these three processes, P0, a scheduler, and P2. So the scheduler is P1. And we've got a logical clock that's ticking forward in these processes. So I put some numbers in there that that shows those options. So you can see that what we can do is, as we are talking from process to process, we can request resources, and you can see that P1 and P2 are both requesting resources of the central scheduler. So the idea is that the scheduler should release the resource in the order in which it was requested. So if P0 makes a request for resource, but that message doesn't arrive until step 6. Meanwhile, it's causally related to P2's request for resource, which arrived at step 5. So that's where this whole idea of the requests being satisfied in the order in which they are made becomes a bit sticky. If you try to solve the problem this way, then you will release the resource to P2 before you release the resource to P1. And that is a problem. That is not the order in which the resource was requested. So we're not going to use a centralized scheduler because that fails to satisfy the second condition, that requests are granted in the order in which they are made, not the order in which they are received. So let's look for a different solution. So here I've got another set of processes with another set of logical clocks, and we can see that they are all communicating with one another, and those clocks satisfy the clock condition. So P0 is going to request the resource, and it's going to do so not by talking to a centralized scheduler, but instead distributing that request out to all the other processes. This is why fixed number of processes is an important constraint on this version of the algorithm. So it's going to talk to all of the potential, or all the other processes, so P1 and P2. And so they're both going to receive that request, and they are going to send a message back to P0. How does this solve the problem? So they are sending a message back that says that they acknowledge the request. So making the request is, first of all, a broadcast, and secondly, it has an acknowledgement component to it. Meanwhile, releasing the resource is a broadcast but doesn't need any acknowledgement. So if P1 has the resource, it's going to broadcast that it's done with it, and that releases it, and both P1 and P2 can see that. So those are the components that we're going to use to build this algorithm. So how does it work? We start with one of the processes owning the resource. That's a necessary starting point for this algorithm to work. So now PI is granted that resource if it has requested the resource, and that request from PI happened before any request from any other process. Every other process has acknowledged that request. So that's also a necessary condition. So if every other process has not, if there's any process that hasn't acknowledged the request, then PI is not granted that resource yet. So let's talk about how this might solve the problem. So you've got P0 requesting the resource. Now, P1 or P2 currently own the resource, and so they both receive that request. They get a causally related clock tick. So they know that their request happened, or that the receipt happened before the send. And then they send their acknowledgments 4 and 5. Now, if P2 at some point earlier had made a request, then that request, and that request is received later, say it's P0's clock tick of 6, then we can now put that 6 in order with the others. So we can see that that it came later. So I didn't do a terribly good job of explaining that part, but let's go through the proof that shows that we can verify locally whether a process has received an event, or whether a process has gained control of a resource. So, process I, does it know that it now owns that resource? Well, it knows its own request, and it knows all competing requests because it acknowledged them. Remember, part of the condition was that every other process has acknowledged the request. So, so therefore, in order for PI to know that a request is actually competing with it, then it knows that it acknowledged those requests. And so all processes can agree on a total ordering. I use the word full ordering. Sometimes I get that mixed up. A total ordering, A is before B if the clock at A is less than the clock at B, or clock at A is equal to the clock at B and the process number is less at I than it is at J, because each one of these processes is distinct, has a distinct process number. Process I executed A before process B. So what we have done here, let's remember back at the beginning, we talked about a topological sort. We talked about finding a total order that satisfies a partial order. This is a topological sort. This is a total order that every process can agree upon. And so using this total order, we can compare the timestamps of the various events to know for sure which event happened first. Now, the requests are probably concurrent. They're probably made without knowledge of the other requests. But yet, this imposes a total order. So that means that even concurrent requests are fully ordered. And that is locally verifiable because all requests for the resource are acknowledged. So, so that means that the process knows the order in which it has, or it knows that the others have received that acknowledgement, and so therefore it knows that they all compute the same total order. So this is the first instance of something that I think is pretty remarkable in Lamport's work. We're trying to prove something globally. We're trying to prove something about the entire distributed system. So we define something that is true globally. And that's the clock. So this particular clock condition, we can't know, a process can't know what's happening on another process. It can't put those events in order until it receives some kind of message, and then it can start to put things together. So this algorithm bakes in the acknowledgement so that you've got that way for systems to synchronize their local clocks. And so now, given just that local information, you can make a decision that everyone will agree upon. So you can prove something about the global state of the distributed system with local information. So the proof knows the global information, but the processes don't. So it's a bit mind-bending, and this is, I would say, the simplest example of this happening. This happens in a much more complicated way in the Paxos algorithm, and so in that one, the same thing happens. You find yourself talking about what the processes know about, and then you make an assumption. You define a term that now no single process could possibly know about, but yet is still true of the whole system. And then you base your proof on that thing that you know is true, and it becomes something that's locally verifiable. It's pretty wild. It's pretty crazy. So that is this idea of local verifiability. So yeah, I definitely suggest reading the paper to get a full sense of it. I don't think I'm giving it quite the treatment it deserves. So this isn't the only thing that Lamport does in this paper. So in addition to showing how a distributed system can share a resource, making sure that only one process has that resource at a time, he also talks about how a distributed system can synchronize its clocks, its physical clocks. So each process maintains a logical clock, CI, and then when CI sends a message to M, it includes the timestamp. When PJ receives M, then it updates, and it uses a particular mu, a particular delta related to that message. And that delta is an estimate of how long between the send and the receive in physical time now. And so this will cause the clocks to synchronize within some tau, some error value. So he spends a little bit more time on that than I just did, but if you make some assumptions about the physical nature of the system, like the fact that you can measure the distance, the time difference between send and receive, then you can synchronize your physical clocks. So that delta tau of d, it floats, but it floats just in one direction. So these clocks get later and later. So yeah, if you really need to have a physical clock that's measuring the time on the Earth at every single machine, that becomes a really difficult problem because that error floats. But this is the starting point for these algorithms that are now baked into operating systems that run in the cloud and synchronize physical clocks on these various machines. But if you really need to know what happened before, and you also have a system that is trying to keep that error bounded, then you probably should build a logical clock into your system in the first place. Okay, there are also some failure conditions that he doesn't really go into in the paper too much, but these happen. These show up later. So he does mention these failure conditions. He just didn't say anything about how to address them. So a failed process is indistinguishable from a slow process. So you just haven't received a message from it. Is it still running, or has it actually failed? So then we also have the problem of network failures. So you might have thought while going through this algorithm here, hey, what if the response doesn't make it back? So I've requested a resource, but the response from P1 doesn't happen at step 4. Well, what do you do about that? He doesn't say. Right now, this is just about networks that don't fail. And then you also have the problem of a process that doesn't play by the rules. So if it doesn't advance its own clock, if it sends messages with the wrong timestamp, it doesn't send acknowledgments, doesn't release the resource, any of these things that the process is supposed to do and the proof is based on, if any of these things are violated, then the proof, the algorithm doesn't work. So these are failure conditions of this algorithm. This algorithm is intended to be a start. Then we go on to these successor papers that resolve some of these problems. So the Byzantine generals paper, that's all about those processes that are deliberately misbehaving. Or maybe they're accidentally misbehaving, but they're not following by the rules. Maybe they just have a bug. Vector clocks, as we saw in here, the logical clock, we were just using a single value, but vector clocks use an entire vector and attach those to values within a distributed database, and that gives you some interesting behaviors. We've got the CAP theorem talking about the the loss of messages and how things can achieve consistency. We've got that communicating sequential processes. That's the term that I was looking for before, that Tony Hoare paper. So here we are talking about processes. They're sequential, they communicate, but CSP is a formal system based on this foundation that lets you prove some more interesting things. Then we get to some of the things that I'm really interested in, and that's things like the fork join causal consistency. So that was a big inspiration to me. And then, of course, historical modeling. My work is derived from what we've got here. So this was one of the really important papers for me, and it appears pretty heavily in the book. And even though I don't in the book go through all of these other things that you can prove with it, I don't even talk about logical clocks. I don't really talk about the steps within processes. What I do talk about is causality, about knowing that something happened before something else, and trying to be a little bit stronger and say, not only do I know it happened before, but also I know that had it not happened, this would be different. And that is where the idea of having predecessors factors in to the historical model. The predecessors are not simply things that happened before, but they are also things that are causally related, things that influenced this decision. And so I'll often talk about facts in a historical model as being decisions, and somebody makes a decision with some knowledge. That knowledge caused them to make this particular decision. So that knowledge is represented by predecessors, and then this decision follows it. The knowledge had to happen before the decision. So you've got that ordering, that partial ordering, but you also have the actual causality. And so you end up with graphs that look like this. I like to flip the arrows so that the arrows point up toward their predecessors, but this is the type of thing that you end up with, being able to model directly from this in a historical model. And that's how a historical model achieves partial ordering. Partial ordering that follows exactly this. Now we can talk about the facts A and B. So A happened before B if A is a predecessor of B, or the transitive property holds. If neither of those two things are true, neither A nor B is a predecessor of the other, and there's no transitive chain that that travels from one to the other in one specific direction, then you can't tell which one happened before. And you get a partial ordering. And then lots of interesting things happen. Lots of interesting things happen without needing to talk about the steps in the processes that cause them to happen. It's really just the facts themselves. So that is how I think about this this paper. Time clocks and the ordering of events in a distributed system. And so I hope you give that paper a shot. Just search for that. You will find the PDF. Give it a read and make a comment. Join me in Discord and let's talk about it. Until then, I will see you next week.